if z is a function f of x, y, then dz, which we can think of as a tiny incremental change in z, is of course equal to df, because f is the same as z. And the df we can write as fx, meaning the x partial derivative of f times the incremental change in x, plus fy times the incremental change in y. And we've seen ample examples of how a change in x combined with the x derivative contributes, along with the change in y and the y derivative, to the change in the value of f or z. Now, the question is, what if x and y happen to both be functions of t, some third variable, so that x equals x of t and y equals y of t? Well, if this is so, then we would certainly expect that if we have a change in the value of t, that's going to change the value of x. And similarly, it's going to change the value of y. So, a change in t causes a change in x. Now, let's go back and along the chain. A change in t causes a change in x, and a change in x causes a change in the value of z. And similarly with y, a change in t changes the value of y, a change in the value of y causes a change in the value of f or z. So in this expression, our dx and dy are both dependent on the change in t. Now, how do they depend on t? Well, the dependence is fairly obvious. Dx equals the rate of change of x with respect to t times the change in t. That is, the change in x is equal to the rate of change of x with respect to t, and that rate of change tells us basically how fast x changes as a result of changing t, and how fast is in quotes here because it's really how fast wouldn't be a negative quantity, and dx dt certainly can be, but this is what it feels like. Okay, this tells you how quickly and in what direction x changes when t changes. So if we take this rate of change of x with respect to t and multiply it by the change in t, certainly then we would expect to find the change in x. And similarly with y, the change in y should be the rate of change of y with respect to t multiplied by the change in t.